Okay, so the next question that we want to answer is, what is this thing? What is this h theta of x here, right? We say at the start that this h theta of x is p of yi equals to 1 given xi, right? So the question is, what is this? We know with hindsight that this is the sigmoid function, okay? But now what we're going to do is to derive the sigmoid function, okay? So let's start. Okay, I'm going to start on a new page. All right, so why the sigmoid function? Okay, so to explain that, I'm going to first introduce a generative process, right? Just like the quick take session that we had previously, we always start by assuming that we have a generative process for the data, and this generative process goes something like that, right? We have something like x here, okay? What we're going to do is first to choose a label for y, right? Just a label y. So that could be equals to 0 or 1. Now, if we choose a label y equals to 0, what we are going to do is to sample from a distribution, right? We're going to assume here, and this is the assumption we make here for the generative process, that we are going to sample from a Gaussian distribution, okay? So this is where y is equals to 0. Similarly, if you choose y equals to I, we're going to sample from a different Gaussian distribution. This time around, could be this Gaussian distribution here, okay, where this is y equals to 1. Right, so in other words, the second step is to sample xi using the normal distributions. And I'm going to say that this normal distribution has mean mu 0 and variance 1. You can actually loosen the assumption that variance is 1, but I'm going to make the simplification that the variance is 1 to make the derivation simpler, right? Similarly, I'm going to assume that this Gaussian distribution has mean mu 1 and variance 1. Okay, so then what we are sampling is essentially from mu of yi variance 1, right? We are sampling from the respective Gaussian distribution. Okay, so now with this in mind, what do we really want, right? Recall what we really want to find is the probability of y equals to 1 given some data x. Okay, so we're going to apply the base rule here, right? If we apply the base rule, what do we get? We're going to get a pretty long expression here. This would be p of x given y equals to 1 times p of y equals to 1 divided by p of x given y equals to 1 times p of y equals to 1 plus p of x given y equals to 0 times p of y equals to 0. Okay, so I'm going to make another assumption here that p of y equals to 0 is equals to p of y is equals to 1 is equals to half, right? So what this assumption is telling is that if we sample a lot of data from the world, the positive data and the negative data has equal chance of being sampled, right? Again, this assumption is not required for the proof to work. I'm just doing it to simplify the proof, okay? You can try it out without doing this assumption. It will still work out at the end, okay? But if we make this assumption, what happens is that this become half, and this become half. We can factorize the half out from the denominator and cancel out with the 1 from the numerator. So what we can do is to cancel out these 3 terms, okay? Because they're all equals to half. Okay, then what we are left with is just p of x given y equals to 1 divided by p of x given y equals to 1 plus p of x given y equals to 0. Okay, now what I'm going to do is to divide the whole term by the numerator, right? So essentially I'm going to divide the numerator by p of x given y equals to 1, which gives me 1, and I'm going to divide the denominator by the same factor. So what I will get is 1 plus p of x given y equals to 0 divided by p of x given y equals to 1. Okay? Now, recall that p of x given y equals to 0 is essentially what's the probability of picking the sample x given that we fix the label y equals to 0. And we already defined it above, right? If we pick y equals to 0, we are picking from the first Gaussian distribution, right? This particular red Gaussian distribution here. And similarly, if we pick y equals to 1, we are picking from this green Gaussian distribution here. So I'm going to do a little bit aside again. Let's do a little bit of aside. Okay. In particular, let's look at this particular quantity, p of, sorry. So we're going to look at p of x given y equals to 0 divided by p of x given y equals to 1. Now, because p of x given y equals 0 is a Gaussian distribution, we can just write down the PDF. Okay. It's going to be a slightly longer expression. So we will have 1 over square of 2 pi. Remember the variance is 1. E to the power of negative x minus mu naught square divided by 2 divided by 1 minus square of 2 pi e to the power of negative x minus mu 1 square divided by 2. Okay? And of course, we can do some very nice cancellation here. We can cancel away this term. Okay? And then combine the exponential term together. So we have e to the power of negative x minus mu naught square plus x minus mu 1 square. And again, the whole thing is divided by 2. Okay. Okay. Now what we're going to do is to do some grind work. We're going to expand the numerator out. Okay, so if you expand the numerator out, what you have is going to be negative x squared plus 2x mu naught minus mu naught squared plus x squared minus 2x mu 1 plus mu 1 squared, right? So this is the term that you get. And then this whole thing is going to be divided by 2. Okay. Now, again, we can do some cancellation. In particular, this x squared and this x squared is cancelled. Now, we just have to combine the term together. And I'm going to combine the term in a very specific way. Okay, I'm going to write it in this way. I'm going to write it as e to the power of, I'm going to write it as e to the power of negative x times 2 mu naught minus mu 1, minus 2 mu 1 divided by 2, right? And then we have minus mu naught square minus mu 1 square divided by 2. Okay? And the reason why I write it in this way is because if we just recall back, the mu naught and mu 1 is actually something that is intrinsic to the word but unknown. In other words, it is something that we can learn as a parameter. So I'm going to set this term right here to data 1, and I'm going to set this term here to data 0. By doing that, what we get here is essentially e to the power of negative data 1x plus data naught, right? In other words, this is e to the power of, this is e to the power of negative data transpose x. Okay, so that's good, right? And recall why we are doing this derivation is essentially to substitute this thing back to here, right? We shift the derivation over here. So now we can go back to here. And let us substitute that back in. What we get is 1 plus e to the power of negative theta transpose x. And voila, this is the sigmoid function that we actually want from the start. Okay, so we have already derived the sigmoid function. So if we go back all the way, recall why we are doing this in the first place, right? We are doing this is because we already defined this previously to be h theta of x, right? So if you go back all the way up to the previous derivation, we say this h theta of x is defined to be p of y equals to 1 given x. And now we have to just derive that this particular thing is just 1 over 1 plus e to the power of negative theta transpose x. Okay, and we are done, right? This is your logistic regression. Okay, so I hope that this video will help you to get a better appreciation of logistic regression. If there's any question, you can put it onto the site, right? I'm like a YouTuber, I'm putting on the site. Okay, so I'll see you next time for a quick take if there are any more. Goodbye.